Should I start now?
Yes, welcome, Dr. Ghosh, to talk about our 100 years of quantum. Welcome, everybody. So this is all yours.
Excellent, excellent. And thank you for having me in this series of talks. And what I'm gonna do today is I'll try to tell you a story, rather not as a physicist that much, but the history is also amazing for this one. So before I begin, a few things regarding the business. So everything I will discuss today, it's going to be my own perspective, and in no way it is going to represent any of my present or former organizations I have remained affiliated with. So that's the number one. Number two is in this format of talk, it's not always easy to engage with the audience. So please feel free to stop me in the middle if you have any question, and we can have some discussion there as well, or you can reach out to me, or definitely we can have question and answers at the end. Okay, great. So as you know, that 2025 was declared as the 100 years of since quantum mechanics was born. It was not clear in the beginning, what do we mean by quantum mechanics was born? And I will try to go from there, and I will try to tell you the story since its birth all the way to the current status of the field. And when I say current status of the field, I will focus more on the macroscopic form of quantum mechanics. You can hear me, right?
Yes, I can hear you.
Okay, and you can see the slides as well.
Yes.
Okay, excellent. So yeah, so this talk will be focused towards the macroscopic form of quantum mechanics, which remains a big push behind quantum computing and many other related areas that you may have seen. So let's start this story, and let's start it from the beginning. So right after John Dalton proposed the atomic theory, the question started emerge that what is going on inside atoms? So if everything is made up of atoms and they are the elemental building block, then why we get so much disparate behavior in the macroscopic world, right? And in order to understand that, we probably need to go inside the atom and understand if there are subatomic particles and how do they behave, what is the mechanics, and etc. Now here I'm showing you two pictures. On the top, this is actually a fused quartz, and at the bottom, this is a silver. So this is just an example of this wide variety of macroscopic behavior that we get to see. As you know, that silver is actually a very good conductor of electricity. Quartz is not. This is an insulator. But if you try to measure the electrical conductivity in silver, you will see that the electrical conductivity at silver, this is 10 to the 24 times more than the electrical conductivity at the quartz. So 10 to the 24 is a big number. It's an Avogadro number, essentially. So what is going on inside the atom so that we have Avogadro number times more conductivity in one material, in one form of material, where the another one is completely insulating the current from flowing, right? So at this point, this is not a very concrete question, but in the mid 19th century, people realized that it is possible to ask some concrete questions based on some data because technology improved and you can actually do some controlled experiment. So one of the experiments, it was done in mid 1850s, like 1860s, by Angstrom. And what he did, he just warmed up hydrogen gas and let it cool down. And when hydrogen was cooling, he observed the various different frequencies that it emits. And it was a surprise at that time because Angstrom noticed that these are some lines. These are not a continuous spectrum that he was expecting that can come out of hydrogen, but it's just some few discrete lines. And in subsequent years, people figured out, Balmer and others, that the separation between these lines, they actually follow an algebraic formula. So nobody understood that what is going on inside hydrogen. So why there are discrete lines, first of all, and what is algebra has to do with hydrogen, right? So similar thing in the late 19th century, Frank Hartz designed this experiment where he actually shone some light on some metal surface like sodium or potassium or cesium, whatever. I think they used a zinc plate here and observed that um, uh, depending on the amount of light that you are using, it actually emits electron that you can measure using a detector on the other side. So this is called the photoelectric effect. And also it was not known that why can light, what light exactly does inside the atom so that electrons come out of the atom and you can detect it on the other side. And similarly, this is one of the most prominent experiment, and also the question was way more clear than many others. It's called the black body. So the concept of black body was introduced by Kirchhoff in mid 19th century, and people did the experiment. For example, this Lamarck-Kurzban experiment happened in the later part of the 19th century, which essentially showed that if you take a black body, and essentially black body here means that, let's say you have a hollow chamber with a single hole on one side. So the idea is that light can go through that hole, but it will reflect so many times before it can come out of this hole, the light actually gets absorbed. So inside the black body, it is always dark, which is why the name is the black body itself. But the light gets absorbed, but it actually emits heat, the radiated heat. And you can measure the frequency of the radiated heat and the amplitude for each of these frequency that you can plot on the vertical axis. Now, when you do that experiment, of course, you will see some peak, like a twisted bell-shaped behavior. But when people try to do the calculation, for example, this Rayleigh-Jeans theory based on the classical understanding of physics using thermodynamics or even the classical laws of Newtonian mechanics, they noticed that something extraordinary is happening. So the theory doesn't make any sense because as you increase the frequency, the theory says that your amplitude actually should diverge, which does not make any sense. Not only experimentally, it doesn't make any sense that how can a finite black body can emit infinite amount of heat for certain frequencies when it goes beyond certain frequencies. So this is a famous phenomenon. It is so famous that in the early textbooks of quantum mechanics started from this point. This is called the ultraviolet catastrophe. Okay, and these are three prominent ones, while there are many others. So for example, I haven't listed here, for example, if you try to see the behavior of specific heat as a function of temperature, then the classical theory suggests that specific heat should be constant, even if you lower the temperature. But beyond a certain point, you will see that the specific heat actually goes down, and nobody knew why. And that's the beginning of some physicists like Einstein or Debye who came into the picture. But there were concrete experiments and there were concrete questions that were asked based on the data that people obtained from those experiments, and nobody had the answer to those questions. Okay, so it was realized at that time. So first of all, these experimental discovery kind of permeated through the entire physics community, and it triggered the theoretical physicists as well to come out of whatever the understanding of physics was at that time. And then people realized it is impossible to accommodate all these experiments with the understanding of physics at that particular time. So probably we have to go beyond, and we have to think beyond. So Max Planck was the first physicist, as we know today, who tried to think beyond and who essentially said, in order to describe this behavior, we have no other option but to say that energy, when it emits, from when it is emitted from some system or when it is absorbed by a system, then we cannot think of that energy in the form of a wave. We have to think of it as a particle. And what it means is it always gets emitted or absorbed in a packet, packet by packet. So each packet has a fixed amount of energy, which is directly proportional to the frequency. And Planck called it quanta. And this is the name that actually came into existence, and people started calling these early ideas as the old quantum theory. Just remember that there is no quantum mechanics yet at that point, and people did not know if all these theories will require or will give rise to a completely different mechanics or not, but new ideas were definitely necessary, right? Similarly, Einstein started thinking about the photoelectric effect, and he realized that there is some value to Max Planck's idea. And if I can really think of light as particles, and in this sense, particle essentially means a physical system which is localized in space and carrying a specific amount of energy. That's all it means. Then there is a heuristic explanation. And that's a very important point because that's how Einstein wrote his first photoelectric effect paper. So that was a heuristic justification, not the theory itself, for the photoelectric effect that was observed in Frank Hertz's experiment. And I must mention here that Indian physicist S.N. Bose had contributed significantly along this line of thought, rather going beyond that light can be thought of as a gas of particles, and you can derive a completely different statistical rules out of it. But that is also a different direction where physics went from this point. But this was a major idea that energy is a packet, not a wave. Bohr, on the other hand, Niels Bohr, Danish physicist, so he also realized that we need more. It's not sufficient if we think about energy in the form of a packet. We have to rather somehow take a stand where classical electrodynamics does not apply for subatomic particles or whatever that is going on inside atoms. We cannot describe that using Maxwell's equations of electromagnetism, because Maxwell's electromagnetism essentially tells us that if there is a charged particle which is orbiting against another charged particle, then energy gets emitted. But if that is true, then it cannot describe the angstroms lines that he was observing coming out of the hydrogen gas. So Niels Bohr is saying that for subatomic particles, something drastic is happening. And therefore, when the negatively charged particle is orbiting the nucleus of the atom, as long as they're orbiting in a specific way, in a specific orbit, whatever the orbit means, then they cannot emit or absorb any energy. And there are only discrete set of orbits, and whenever they jump from one orbit to another one, and that's exactly the point when Einstein's and Max Planck's interpretation of energy comes into the picture, so they can absorb exactly that much amount of energy, which is the energy difference between those orbits. These were all revolutionary, by the way, at that time, because not only the classical understanding of physics couldn't explain the experiment, but also the definition of the physical systems require modifications, right? But even at that time, we cannot say that this is the birth of quantum mechanics because there is no mechanics. There are some heuristic justifications. There are some new ideas that started coming in. Okay, now this is a point, and that, as you can understand, that took quite a bit of time, and people constantly did many different experiments and constant discussions and etc. That is essentially the history for first 25 years in the 20th century, starting from all the way to 1900 when Planck came up with the Planck law. and all the way to 1925. But this is a major idea that I must spend some time on. So it was known from some experiments in very early 19th century that were done on light, that light actually demonstrate the wave nature, right? Because in the beginning, there were some linear optics, or we know that there are some properties of the light that we can understand without invoking their wave nature. For example, reflection and refraction, etc. But there is something called interference. So what happens in this experiment is, if you shine light on a double slit, then each of these slits act as an independent source of your light. And as you can see, that when the light is coming out of these two slits, they constructively and destructively interfere, and therefore you will be able to see an interference pattern if there is a screen at the back. Now, that is well known, and that is very well understood from the wave theory of light, right? Because wave is not localized in space, and it can take positive and negative values. So you can clearly demonstrate that why there is an interference pattern. Now, it was understood, although the experiment was not done, after the whole quantum theory evolved, that if you try to do this experiment, not with light, but with a beam of electrons, probably you will be able to see the interference pattern. But it didn't make any sense, right? So what it means is, if we did not have those weird outcomes from this experiment, if you just shine electron beam against the two slits, and if you think of electron as a matter, as a particle, then either the electron will go through the left slit or the right slit, and you will be able to see two lines. But that did not really happen. So this experiment was conceived by Max Born and in his team, I think in 1920s, but there were some technical difficulties, and finally it was verified in an experiment in 1927. But the understanding was there that probably this is where we are heading at. It doesn't matter if I do this experiment with light or with a beam of electron. In this setting, they will demonstrate the interference-like pattern. Now, there is actually more to it, and I'm not going to go too far down the line. So, for example, instead of shining a beam of electron, if you make sure that you are sending one electron at a time, the technology was not there at that point, but if you do it, what will happen then? Are you still going to observe this interference-like behavior? Or you will see two lines? That is question number one. Question number two was, for the light experiment, instead of shining light this way, if you somehow able to send one light particle at a time, often called photons, will you still observe the interference pattern, or there will be two lines? So, of course, the experiments were not done, but de Broglie was the first physicist who realized it doesn't matter how you do that experiment, like one particle at a time or just shining an entire beam, there will always be an interference pattern. And de Broglie had done something amazing. He first ensured that there is some apparatus in physics that can accommodate this. And in order to do that, he actually combined these two ideas. One came from Einstein, another came from Max Planck, with this beautiful equation called the de Broglie equation, right? So what it says is, every matter has a wave-like behavior, and wave can be thought of as a matter as well. It depends on what type of experimental setup that you have. So Einstein was formulating a new mechanics at that time called relativity, or special theory of relativity. And he was formulating the four momentum and all sort of four vector, the differential geometric definition of the Newtonian mechanics. And this four momentum formulation was very popular because one of the component actually gave rise to the famous Cult equation, equals to mc square, which itself created a history after Second World War. But this momentum is actually coming from Einstein's formulation of the four momentum. On the other hand, Max Planck had that idea that energy is always comes in the form of a packet, and every packet has its own frequency or wavelength. So this lambda is actually the wavelength for that packet, and that is connected to the energy. And energy is just one component of the four momentum, and this P is the momentum. De Broglie actually equated this thing in this relationship. And this identified the new experiment in the light of the matter-wave duality. So every matter can be thought of as a wave, and wave, depending on the experiment, behaves like matter. But before I move on to the next, just think about it. There are some phenomenal consequences if we are forced to adopt this picture. Wave on one side is not localized at space, right? And it propagates through a space as a function of time. And if I have to think matter in the same way, does it mean that matter, there will be some experiments where matter itself is not localized at space, and there will always be a probability to find a particle in different space point for a specific matter? And what does it even mean? So all these things are hidden, are buried inside this equation. And therefore, this was actually a fundamental cornerstone of a very different way of thinking. I'll come back to this point, but just know that this is very unintuitive. And even from philosophical perspective, it challenged our perspective, the way we perceive matter and wave separately. Okay, so so by the way, this equation, de Broglie's formulation, was done in 1924, and inspired by this new approach that there is a way to connect the behavior of matter and the behavior of wave through an equation. Two young physicists started a program to describe all the previous experiments that came for the quantum theory. So all the previous quantum mechanical experiments that were done. One of them is Heisenberg, the German physicist, and I think he was unwell, and he went to an island, and then he came back with his approach called matrix mechanics. It was done in 1925, where Heisenberg actually focused on the experimental setup. What is exactly the physical system, how you are preparing it, how you are evolving it, and what exactly are you measuring? These entire component and the various combination of those can be thought of using some linear algebra equations, often termed as matrix. And he came up with some equation that describes everything in terms of that particular experiment. On the other side, Schrödinger, although the paper wasn't published until 1926, but there are some evidence, and I have tried to collect a few of them, that the scribblings, that the main ideas were constructed in 1925. He was heavily relying on de Broglie's idea about the matter wave. And he was trying to find a wave equation for matter. And that is exactly the equation that we know today as the Schrödinger equation that described the quantum dynamics. So these were very two different approaches. The question is, which one was right? And it was not known in 1925, and Heisenberg definitely thought that his matrix mechanics was right, and then the Schrödinger's wave mechanics was not. But it seems that there is a very simple question one can ask in order to settle that. So the question is, which one can explain Angstrom's discrete lines for the hydrogen atom, right? And that's what happened in 1926, where two papers were published, one from Pauli, and after 10 days, this one from Schrödinger himself, where they both applied their, Pauli actually applied Heisenberg's approach, and Schrödinger applied his own approach for the hydrogen atom. And they both gave rise to the same numbers and explained these discrete lines that Einstein observed, and also realized that why there is an algebraic behavior that coming out from this theory. So Schrödinger actually went beyond, and he showed at the later part of his paper that matrix mechanics and wave mechanics, they are exactly identical. They are different formulation of a same theory. And for convenience, let's call it quantum mechanics. Okay, so this is the name appeared in 1926. The work was done in 1925, which probably makes sense that why 1925 can be thought of as a birth point for this new, not only this new thought process, but also these mechanics that can replace Newtonian mechanics completely for subatomic particles. Good. So far so good. So this now we have to make sure that everybody is on the same page, right? Because quantum mechanics is a very new thing, and of course it managed to describe the experiments that happened until that point, but it was necessary to ensure that different perspectives from all the different areas in physics, they agree with this new revolution, essentially. So the fifth Solvay conference, one of the most famous Solvay conferences that was organized in 1927, and almost all the well-known physicists at that time, they showed up. And after a long, exciting discussions, Max Born and Heisenberg and most of the proponents of the quantum theory or quantum mechanics, they declared that the revolution is over. We have two different forms of mechanics, matrix mechanics and the wave mechanics, and they converge to the same one. So we kind of rewrite the quantum mechanics in a more generic form, and we got the theory. So this can explain everything for the smaller systems, for the microscopic systems. The problem was that Einstein did not agree with that. And the very reason Einstein did not agree is something to do with what I was trying to emphasize with de Broglie's equation. So Einstein realized that there will be some drastic consequences of if you try to connect the wavelength with a momentum through de Broglie's equation. There might be situations that won't make any sense, where matter can exist at different points at the same time, and etc. Einstein did not know how to ask a concrete question and what exactly was the question, but he had a doubt that probably this is not the way physics was done at that time. And that was the beginning of the famous Bohr-Einstein debate that started from 1927. Okay, now during the time 1927 to 1935, that was a very crucial time, because 1935 Einstein was ready to ask a very concrete question. So proposing a very concrete experiment that one can do, and one can clearly see the point that he was trying to make. So during this time, Einstein had relationship with the scientific collaborative relationship with Schrödinger. And those letters were discovered later. And they're actually asset of the history of physics at this point. So the first question is, why such a long time, 1927 to 1935? So the first thing is, this philosophical perspective is deep. That's number one. Number two is, that was a very troubling time at that point. Remember, that's the time when Nazi power came to the rise in Germany. They all had to flee. Essentially, Einstein relocated to Princeton and took his position at Institute of Advanced Studies and etc. So it was also the geopolitical issues that affected science at that time. But in 1935, Einstein published his seminal paper with Podolsky and Rosen, and they said that if the quantum mechanics is true, one of the consequences is you cannot determine the position and momentum of a same particle at that time. That was known as Heisenberg's uncertainty principle, and which is understandable for wave, which is delocalized anyway, but not that much for particle. But that's fine. We can still assume. But Einstein pointed out a completely different problem. Einstein said, what will happen if I send an entangled particle? What it means is two copies of the same particle, which has the same property, in two different directions in 180 degrees. So for example, from the Z point, you are sending one of them, one copy of the particle on the left, another one on the right. And then I can measure the position of the left one and the momentum for the right one. But I know by symmetry that if I just sign invert them, I can get the position and momentum for both. So that was the original proposal. Of course, that experiment was hard to do, but finally it turned out that there is a way to perform an experiment that is very similar to it, but it took a long time, and Einstein didn't see the outcome of this experiment during his lifetime. But the question was clear, that how do I make sense of the outcome of this experiment? People realized that if quantum mechanics is true, then when you are measuring the position of the first particle, something must have happened on the second one at the right, so that the position of that particle becomes uncertain. But then it brings a bigger question that what is the time lag between your measurement of particle A and something is happening with the particle B? So Einstein pointed out that this time lag has to be zero. Now, if it is zero, isn't it violating his own special theory of relativity, that there is some superluminal connection between the particle A and the particle B, which is spatially separated? So these are all the deeper questions that arose from Einstein's way of understanding it, and often known as the EPR paradox. So that is number one. The number two is, and that is not between Einstein and Bohr, that is between Einstein and Schrödinger. Einstein also figured out that if quantum mechanics is true, then probably you can couple smaller system to some bigger, and then that's some bigger system to an even bigger system, and you can translate it so that quantum superposition, which means that a particle can stay at the same time in different location, you can make it true for macroscopic systems as well. Schrödinger made this very concrete, introducing his analog concept of Schrödinger's cat. And what they said is, you can put a cat in a box and then probably a cyanide chamber there, and you can turn the cyanide chamber on and off using a radioactive particle. But the radioactive particle, if that's quantum in nature, there is some probability that the cyanide chamber is triggered versus it's not. But if it's in a superposition, then the cat itself in the superposition of being alive and being dead. And Schrödinger said, okay, this is getting complicated. I don't know anything about quantum mechanics for macroscopic world. All I know that it will work with the subatomic particle. I have no idea what will happen if you do that experiment, but that came at that same time. And the question was unresolved, but nobody knew the implication of the absurd behavior of quantum mechanics at the subatomic particle, how that gets translated to macroscopic systems. Okay, so very quickly, this is important for the history of physics. So in the fifth Solvay conference, of course, there are questions raised by Einstein, and during the time 1927 to 1935, as we have seen, there are paradoxes that evolved between Einstein and Bohr, and also the paradoxes that one can think of connecting microscopic with macroscopic, right? So, but there were some progress that made as well. So in 1927 conference, an interpretation of quantum mechanics was born, often known as the Copenhagen interpretation. And most prominent physicists at that time, they accepted it. They accepted it philosophically, and also they accepted it what is referred to as praxeologically. What it means is you can make use of it. You can use these equations to explain experiments, and you can use those equations to build bigger theories. And this is how the entire landscape looked. And there are various different branches that came out of this early version of quantum mechanics. So the leftmost branch is Einstein's own branch, because he did not believe in quantum mechanics, or he didn't think quantum mechanics as a complete theory. He thought that there must be some other theory that will give rise to quantum mechanics, but more deterministic in nature. So he was busy in combining his general theory of relativity with Maxwell's electrodynamics. So this is his own branch, and he is probably the only person working on that one at that time. The rightmost is the usual progress that you may see in the popular science, which went all the way to Higgs boson. And it came after Dirac said that special relativity can be combined with quantum mechanics in 1928. And that opened up the possibilities to formulate a quantum theory of electromagnetic radiation, which is called quantum electrodynamics. That was done by Feynman, Swinger, and others. And some other fundamental forces of nature were known, and they were subsequently described using a very similar approach by Electroweak and QCD, etc. So this is a very well-known thing that we often get to see in various popular explanations of physics. And this is known as the standard model. This is the standard model for particle physics, by the way. So the standard model doesn't mean that it can explain all the condensed matter behavior and everything. This is the standard model for subatomic particles for the high energy physics that we get to see. There is, since I said that right after Copenhagen interpretation, there were still some doubts which actually give rise to this EPR, the Einstein-Podolsky-Rosen. That is a beginning of a foundational branch where people wanted to formulate that experiment so that it can be done, and the Bell inequality and etc. So this is a more like a foundational branch. The red segment is showing this is a branch that is collaborating with computer science a lot, and this is where the quantum information theory or quantum computing fits in. I'm not going to talk much about that today, although this is the area, and this is also the area where I work on. But this came through Feynman and others who realized that, yeah, quantum mechanics is absurd, but you can make use of it in other sense. You can create a device using particles following quantum mechanics so that it can simulate other particles that are following quantum mechanics, which is very hard to simulate in a classical computer. So that's what this quantum information. Now, this intermediate section is related to the evolution of condensed matter, and finally, very much related to the Nobel Prize that went in 2025 this year for demonstrating macroscopic quantum mechanics. So we talked about Schrödinger cat, which was formulated by Schrödinger through his letters with Einstein. But there were some developments that happened. So for example, superfluidity and superconductivity, those became the spotlight in the mid-20th century. And people realized that there are some superfluidity, for example, the helium-3 superfluidity, and also in almost all superconducting materials, the current is not being carried by electrons. The current is being carried by an atom, but that's a weird atom made up of 2 electrons. I'll come back to that later on. And so first of all, what do we mean by atom by 2 electrons? Because they should repel each other. But anyway, but yeah, that's a weird part of the superconductivity in general, where a macroscopic phenomena is supported by something that can only be understood using quantum mechanics into the picture. So in 1962, there's a young physicist, Josephson, who realized that using quantum mechanics, of course, it is possible to show that those electrons forming pairs responsible for supercurrent, they can actually pass through an insulating barrier. So he actually calculated that. That was not an experiment yet. It was an experiment in 1963, but you can calculate that. And Josephson did not realize that the consequences of it. He just thought it's a weird idea that it can pass through a barrier which has a higher potential energy, but that is another weird effect of quantum mechanics. What it says is if you enclose a particle in a box where the kinetic energy of the particle is less than the potential energy required to penetrate through the box, in the classical world, the particle will always remain in the box, right? If I'm inside a prison, I cannot probably go out of the prison using my own kinetic energy. The classical mechanics doesn't let it happen. But in the quantum world, even if the kinetic energy is small, it can impart that kinetic energy on the wall where the potential energy is, and there is a tiny probability it can come out of it without breaking the jail, essentially. So it's called the quantum tunneling, and that's the idea that he applied. So all these ideas essentially re-triggered the Schrodinger's original idea of creating a Schrodinger cat. Now, Schrodinger cat essentially means that it's a macroscopic object in two different states that are macroscopically distinguishable. And either you are creating a superposition of these two states, or you are showing that there is a quantum mechanical tunneling that can happen from one state to another. And this is the beginning of something called macroscopic quantum mechanics. But this is the deeper point that I have to emphasize. And all these ideas were formulated and made rigorous by Anthony Luggett, who was a Nobel laureate for helium-3 superfluidity. And that is the point that we have to emphasize. Okay, so this is a seminal paper that Tony Luggett wrote in 1980. It's the first time Luggett asked this question in the later part of 1978, and the question was very simple: that what is macroscopic quantum mechanics, and why is it weird, and how we can observe that? The question is a little deeper because every object, so there is a way at that time people understood that there is a correspondence principle. So quantum mechanics is true in the classical limit. It actually converges to Newtonian mechanics or even statistical mechanics, depending on your problem statement. And in the classical world that we are living, this is a noisy quantum world. So can that be called as a macroscopic quantum world? So that's not entirely true. So this is a deeper point that Tony Luggett was making. He was reinterpreting Schrodinger's original idea of Schrodinger cat. So let's see what is the deal here. So Luggett noticed that, let's say there are Avogadro number of particles, n number of particles, n is the Avogadro number, and each of these particles are following quantum mechanics. Then for each of these particles, I can assign a wave, and there will be a wave equation if I look at the Schrodinger's formulation. So let's say this psi1, psi2, and etc. These denote the wave nature for each of these particles. And I can combine them and I can assign a wave-like behavior for the entire system comprising this n number of particles, right? Now, I'm avoiding some technical difficulties here, but if it is true, in order for it to be true that the entire system of the Avogadro number of particles behaving quantum mechanically, they have to share a same wave function. Now, there are multiple ways they can share the same wave function. One way of doing that is called the product states, where if you do a measurement on one particle, it does not perturb this entire system. So it does not, this measurement does not permeate its effect to the entire system. So the entire wave function doesn't even collapse. But there is another way of thinking about it, where you can prepare a state for this bigger system in such a way so that if you measure one particle, it can actually perturb the entire system. So the state of the entire macroscopic system is projected to one of the possible states. And that's where Schrodinger cat is. That's the real description of Schrodinger cat for the macroscopic world. So Luggett pointed out that macroscopic quantum mechanics is not merely a macroscopic number of particles or microscopic systems following quantum mechanics. There is a difference. This is actually quite deep. I'm not gonna go because Luggett actually had to introduce some technical tools like reduced density function, etc., in order to establish his point. But just to know that the summary here is in order to demonstrate that you are observing quantum mechanics in the macroscopic level. First, yes, you have to prepare a macroscopically distinguishable states for a macroscopic system. And then you have to show that either you can create a superposition or you can perform a tunneling between these two macroscopic states. So that's the summary. Okay, so looking at the time, so Luggett realized that whatever the status of the physics at that time, there were superfluidity, there was superfluidity, and there was superconductivity. For some reason, Luggett thought that superconductivity had a better prospect in order to demonstrate macroscopic quantum. So, and that is because something called the Josephson effect that we touched upon. Just to remind you that if you have two superconductors with the insulated barrier inside, which is the red part, then the supercurrent actually can flow through this insulating barrier. That's what Josephson discovered. Now, supercurrent, as we just said, that they are not carried by electrons, they are carried by a bound state between two electrons called Cooper pair. I'm not going to go into the detail how they create a bound state here, and that alone is a different topic. But these Cooper pairs follow a completely different rule than electrons. So just a little bit technical. So electrons follow a specific statistics called Fermi statistics, while the Cooper pair, they actually follow the Bose statistics. And there is something inside the Bose statistics that allow them to behave in a macroscopic quantum system. So all the Cooper pairs together, Avogadro number of Cooper pairs, just like from my previous slide, they actually behave like a macroscopic quantum system, and you can assign them a wave function. And therefore, the wave function on the left and on the right, there is a phase difference. And that phase, which Josephson denoted the small phi here, follows this equation that he derived. But if you think about this phase is not a property of a specific Cooper pair, nor it is a property of a microscopic particle. This is a property of a macroscopic system created out of Avogadro number of Cooper pairs. And they are following quantum mechanical rules. Okay, so that's the difference. Okay, now very quickly aligning with the history at this point. Josephson, when he discovered that effect, there was another graduate student under Brian Pippert who was also a supervisor for Josephson. His name is John Clark. By the way, he is one of the Nobel Laureate into 2025 this year. So, and he knew Josephson, and he always thought about thinking about this experiment. However, the Josephson experiments were done by Anderson and others in the Bell Lab in the next year, 1963. People started making equipments out of it. For example, the squid, which can detect the tiny magnetic field, that was done in 1964 from the Ford research lab. And on the theory side, it was necessary to describe quantum mechanics for this macroscopic system because the textbooks were not written that way. And how you can take the Josephson junction and then create the quantum mechanical equation out of it. So these textbooks started appearing in early 1970s. So here is a picture from one such textbooks where quantum mechanics was not necessarily formulated for subatomic particles, but formulated as an LC circuit, and when and how you can see quantum mechanics out of it. So again, to understand the experiment very quickly, what it means is if you take an electrical circuit, like an LC circuit, so it was understood from the classical electrical engineering that this behaves like a harmonic oscillator, because Kirchhoff's law actually tells you that the charge itself follows the same equation that harmonic oscillator follows, right? And therefore, if you view this circuit in the quantum limit, what it will mean is you take this circuit, put it into a dilution refrigerator, and cool it down all the way to 10 millikelvin so that your wave function is not perturbed by the thermal fluctuation. Quantum mechanics says that the energy level of the harmonic oscillator, just like atom, they are quantized. So, and the transition can happen between these, but they are quantized harmonically. So you should be able to see the same thing for such circuit, and that can be observed. And for theory side, if you can take the Kirchhoff's law and you can promote their charge and the flux to operators, just like you do your position and momentum in quantum mechanics, and apply these Dirac's rule that they are connected by the Planck's constant, and that can allow you to do quantum mechanics with the electrical engineering components. And you will be able to see that the quantization happens there too. Okay, now we are almost ready to describe the experiment that was done by the trio for the macroscopic. This is the final piece. So inductor and capacitor, of course, there's a resistance. We are not going to talk about it, but inductor and capacitor are fundamental building block for the electrical engineering, but they are not sufficient because they are linear things and you cannot distinguish the photon and etc. So Josephson discovery opened up this possibility of taking a Josephson junction as an electrical engineering component. And as Josephson showed, that they actually follow this equation. What it means is if you take a Josephson junction and apply a bias current across the Josephson junction, the potential energy, unlike the potential energy of the harmonic oscillator, you will see a wave-like, a tilted wave-like behavior. This is called the tilted washboard potential. The point is you can actually control a parameter, for example, the critical current here, so that you can tilt it further. Now, so Luggett and others realized that every metastable state, every local minima here, they actually correspond to some metastable state corresponding to different macroscopic configuration of a macroscopic quantum system. So once you can show that you can prepare such a system in superposition in two different potential well in the local minima, that is going to be a signature for macroscopic quantum system. That experiment was not that easy, but even if you can show that your state can tunnel through from one minima to the next minima, you can distinguish that from a voltage that is coming out of the circuit, but that will also signify a macroscopic quantum system because you are observing a macroscopic quantum tunneling. But you need to absolutely make sure that this tunneling is happening through a quantum mechanical fluctuation, not a thermal fluctuation. So let's now look at the experiment that was done in 1985, which was the main theme for this year's Nobel. So what they had done, this is an ingenious data visualization, by the way. So this is the final result. Let me help you through how to read it. So they actually defined two different temperatures. So these are just parameters. So each and every point on the left-hand side denotes a tunneling from one metastable state to another metastable state. Not all of them denote the tunneling due to quantum mechanical, like the quantum tunneling, but they denote the tunneling. The point is that if your dots, like field circles or the open circle on this line, on this diagonal line, then this tunneling is happening by temperature, by thermal fluctuation. That's not what you are after. So if tunneling has to happen through quantum fluctuation. This tunneling rate on the y-axis should be completely independent of the tunneling on the x-axis. So you are expecting a horizontal feature, and that is exactly happening in this regime. So once you cool down your temperature, your system beyond a certain temperature, your thermal fluctuation gets smaller than the plasma frequency of the system, and you will see that there is a horizontal trend. And that means the tunneling behavior is completely independent of thermal fluctuation. So these tunneling cannot happen due to thermal. They must have happened through quantum. So that is something that they pointed out without any free parameter. And that was a big deal in 1985. So I have only 5 minutes left. So these actually opened a floodgate. What it happens in the next 15 years, people figured out all sort of macroscopic quantum systems one can make using these Josephson junctions and other electrical engineering circuit components, and observed all sort of macroscopically distinguishable states. For example, the circulating, the clockwise rotating current versus anti-clockwise rotating current in the squid in superposition. So these all satisfy the Lagrange's dream, the Lagrange's criteria of that macroscopic quantum system. People very soon realize that this is not only a cat. This is not only a question of philosophy. You can think of such circuit as an artificial atom. Before that point, people know that atom can only exist naturally, right? They're given by nature. So these actually also opened up the possibility where you can fabricate these atoms in the lab, you can control them. So you can control them so that they become like hydrogen atom or helium atom or something like that. So this is a completely new direction. And of course, there is something called quantum computing that has more capability than classical, but you need a completely different bit called qubit. You can create a qubit out of this electrical component as well. And this was the beginning of the first superconducting qubit that happened in the next 10 years, where different qubits were formed and people tried to do experiment. All these qubits actually showed extraordinary behavior of quantum mechanics at the macroscopic level, but none of them are good for making a quantum computer because they are not coherent for a long time. So the thermal fluctuation break their quantum mechanical property in a very short amount of time. So we needed a breakthrough at this point. On the other hand, as I mentioned, that it's a chemist's perspective when they say the atoms and atoms combine together, make molecules, and etc. Physicist's perspective of an atom is it's a fundamental building block that interacts with light, right? So that if I know how to create an artificial atom, I must have a way to interact them with light. So this is called the circuit quantum electrodynamics, initially proposed in the early 2000s. And finally, this Geller and Cleland proposal and others, they actually figured out how you can couple a superconducting artificial atom with a resonator through a chamber where there is a light and make them interact. And this opened up this direction called the circuit QED. When EL demonstrated in 2004, that can be done, and you can do quantum optics entirely in this new area, for circuit QED systems. I was talking about a breakthrough that was needed for qubits to become a building block for a quantum computer. The qubits has to be good. So that happened in 2007. Idea was simple, that LC oscillator, and we have seen that it gives rise to a harmonic oscillator. People knew Josephson junction is a nonlinear inductor. So how about if I take a Josephson junction, shunt it with a big capacitance, that should give us a better nonlinear inductor. So that was the original idea. And this turned out extremely coherent than many other qubits that were prepared earlier. And this is called a transmon. This is assumed to be the fundamental quantum computing effort that go into it as the field stands today. So this is, again, 2007. So this is how it looks. Michel Deveray and John Martinis, they came out of the Berkeley lab from John Clark. They joined different universities, Yale and UCSB. They created their own groups. and collaborating with the theorists. And finally, during 2007 through 2013, systematically people made a huge development, which was shown in the lower right corner, where the coherence time increased in a exponential, in a log plot, essentially, in the number of years. And all these can be thought of as various different superconducting artificial. You can think of this entire picture as a periodic table for, like Mendeleev's periodic table for artificial atoms. I don't have time to go over this entire thing. Building a quantum computer, as I have said, a big push, but it required one to couple these qubits, these circuits, superconducting circuits, in a very proper fashion where the environmental noise doesn't take into effect. And that required a very complicated math. And it was developed starting from 2000. And finally, people realized it in the early 2011, 2012. And this is called the topological codes or the surface code, which is a paradigm where various different companies are proposing their own milestones. I don't want to go over this one as well. This is the question of optimal quantum control, which is heavily done in the research area, in the frontier, how you can control these circuits so that even at the rudimentary level, a significant amount of noise is screened so that you can fit it to a bigger picture where the quantum computer can calculate something that is not erroneous. So this is, and this is the area where different protocols are used by different companies as well. The point is that, that one discovery opens up this huge field that was pursued by this entire industry sector with multi-billion-dollar investment throughout the globe. That includes the giants like Google and IBM as well. And this is very relevant in 2025 because as United Nations declared, this is the quantum science and technology. Just one thing that I point out, that this is a field that also requires some accountability from scientists as well. There will be hypes, and there are. It is important that we report what we see, and we bank on the experimental evidence and move our technology forward. So that's why we should go back to the basic principles of science and how science was built. I think that's all I have. Thank you.
First of all, thank you for the great talk. And I noticed Michael and Terry, he has a discussion. And actually, I noticed Terry Bollinger has a question.
Sure.
Terry, can you unmute?
Can you read that question?
Sure. Terry, can you unmute and ask the question?
Hello. I'm not sure. I've made several comments. Helen, can you tell me which comment you're referring to?
I noticed you have a question mark. Whether Schrodinger's cat is solved depends on which community looks at it. Since many world folks discuss the existence of detection, they say, no, this doesn't happen. It's always expanding in superposition. Other interpretation of them, including MWI, really have the problem of definition. What exactly is an observation?
Yes. If I had to boil that down into a question, any comment, by the way, great presentation. That was a very nice summary of the background. Really enjoyed that. Any
Thank you.
observations you might have on this interesting issue about observation? Because so many parts of quantum theory go back to that issue. And the distinctions between the Everett interpretation, the de Broglie, Bohmian interpretation, all of those have components of observation. So your thoughts on that?
Right. So this is the well-known quantum measurement problem. And just for the broader audience, let me reinterpret the question a little bit like this. If I have a subatomic particle, let's say a microscopic particle following quantum mechanics, then I know absurd things happen. For example, superposition. Now, measurement, on the other hand, is a bridge between microscopic and macroscopic, because end of the day, your measurement apparatus is a classical device. Then the question is, if I create a system of chained measurement, for example, I take a small subatomic particle, I couple it to a little bigger system, and then that to be a little bigger system, and etc., then each of these systems, if I move continuously, should follow quantum mechanics. Then why we need a different mechanism in order to describe quantum measurement? Why can't it be accommodated inside Schrodinger equation or Heisenberg formalism and etc.? The first thing is the answer to that question is not known. This is still an open question philosophically, and also one can make a very concrete, rigorous physical statement about it. None of these are known. This is one of the most important open problems. That is number one. The number two is, even if that measurement happens, where does it break the boundary between macroscopic versus microscopic, right? Isn't it continuous? Isn't it a continuous journey of scale when we move from microscopic to macroscopic? That is part of the measurement problem as well. The answer is not known. Now, the question about the interpretation. There are different interpretations that emerge, and one of them that you mentioned, the Bohmian mechanics, which I think appeared in 1960s, sometime in 1960s.
Roughly.
So the problem with, the Bohmian mechanics is probably one way to think about how quantum mechanics works, but the problem is Bohmian mechanics cannot solve this problem. There is a concept of non-local pilot wave. It is very similar. It will create the similar philosophical problem that you have with non-local matter. You are essentially replacing it with a non-local wave, which is the non-local potential. And all these issues that exist in the measurement will remain there. Hugh Everett had a different interpretation for the multiverse. So what I will say that there is a way to make sense of Copenhagen interpretation philosophically as well. What it means is, and I don't want to go too technical here, but what it means is the bigger difficulty is to understand the particles exist in the Hilbert space, which is not only infinite dimensional, but the dimensions are continuous. And the real space forms a basis of the Hilbert space, and that is the biggest difficulty. And there is a way to think about systematically in the smaller discrete systems where the Hilbert space itself is discrete, for example, the spin systems and etc., and make use of the Copenhagen. When you go to the continuous problem, I'm not sure if Hugh Everett's multiverse is offering you a bigger benefit over Copenhagen or not. But in any sense, I think it is kind of understood by the broader community that there are supreme questions that are not answered by any of these interpretations. And Copenhagen interpretation, at least, is more connected to the equations that we use to apply quantum mechanics. So let's go with it. But of course, this is an open area.
Just to comment on it, it's interesting how the Bohmian interpretation, when I read the older papers on that, they didn't have that superluminal component, but now it's very common to see the idea that the wave itself essentially recreates the problem of instantaneous interaction that troubled Einstein so much. So it's interesting to see. And I think there's a mathematical equivalence that you don't really wind up solving that problem. You just transfer it to the wave function. And then you have this interesting, still had this interesting issue that Einstein himself was so concerned about. So thank you.
Right. Just a quick comment here. The superluminal communication. So Bohmian. I'm not an expert on Bohmian, but the thing, and I don't think this is very widely because after the discovery of the non-local potential, many conventional quantum theorists saw the same issues that Copenhagen is suffering from. But superluminal communication is very important. It was an open for quite a while until the information theory evolved. And finally, people realized that how Copenhagen interpretation is not in conflict with special relativity. So even if you do quantum teleportation, then between Alice and Bob, you need a classical channel between Alice and Bob in order to communicate the outcome for the result that they are observing. Without the classical channel, that teleportation is not complete. Now, every classical channel obeys subluminal relativistic consideration. So that is what is saving quantum teleportation from the superluminal assumptions that might arise. So that is number one. But there was also another one, which is related to something called the no cloning theorem. So quantum mechanics does not allow you to clone a quantum state, an arbitrary quantum state from one system to another. You can show that pretty easily, because if you could do that, then that is not going to be unitary. So you will violate Schrodinger equation. Initially, people thought that quantum teleportation might violate that, but all these things are settled under the red branch that I was showing with the advent of quantum information theory.
Can I make a couple of comments?
Sure.
Because I brought up the Bohmian, the de Broglie and Bromian interpretations, which are not totally correct, just as Copenhagen is not totally correct. I think one of the problems is that that they're both non-relativistic theories, and that's why many of the assumptions are incorrect, and that's why many of the solutions, I believe, are incorrect. Quantum field theory does a lot to clean this up. And perhaps you can comment on that. But also, some of these interpretations are utterly ridiculous. First of all, the observation issue, that the outcome depends on the observers. Surely we had a universe and physics as we know it before there were observers, so to speak. Certainly before there were intellectual, technological observers. Just a comment. I mean, I put this in the chat, but a comment on the many worlds interpretation. Even Hugh Everett, later in life, said, "I was kind of putting my professors on with all this," and the many worlds interpretation is not science, for the very simple reason is that it can't be tested. Anything that cannot be tested is not science. Right. And I would put string theory in that category too. Any comments?
So when you say that multiverse theory cannot be tested, I think what you mean is you cannot devise an experiment that can distinguish Copenhagen interpretation from the multiverse interpretation of quantum mechanics. So from that perspective, yes, it does not satisfy the falsifiability criteria science is built up to, right? So at least the way we know it today. However, this particular comment that is it true that measurement problem remains an open problem for Copenhagen, multiverse, Bohmian mechanics, or any other that you can imagine, if this statement itself is a scientific statement or not, I don't know. I mean, if there is can you devise an experiment to show that measurement problem remains a problem in Copenhagen as well as in multiverse? I don't know if people have worked along that direction, because it's just because of the history. So just the way the theory goes, it looked so absurd end of the day in the format when we are doing the measurement itself, that people automatically assume that the underlying theory must accommodate that absurdity, whatever the interpretation is. So, and it is good in that sense that it's an open problem, because in order for it to close, you have to check many boxes involving the criteria of falsifiability.
But many of these problems stem from false assumptions that Copenhagen theory makes. The most basic assumption is that we're dealing with particles. Particles are a macroscopic concept. I don't believe there's any such thing as a particle on the atomic scale, as quantum field theory shows. I mean, everything is a wave. There's no such thing as a particle. And once you assume particles as having to be at a point in space and time, then you come up with all these paradoxes. And this is the problem, many of which, as I said, have been resolved by quantum field theories. But yet they still teach Copenhagen theory as if it's gospel, and I think this is a mistake and it's misleading.
Okay, here is what I'll say. First of all, Copenhagen is an interpretation for some equations that axiologically people use to describe experiments that behaved quantum mechanically, or to develop a technology that you can develop using quantum mechanical systems. So Copenhagen interpretation attempts to assign a meaning to some of the variables in those equations. For example, the psi of x in Schrodinger equation. Now, if we are trying to create an educational model on Copenhagen system, I don't think we should use either the word particle or wave, because it does not corroborate to any of them as you suggested. So the bigger challenge is we first have to break the barrier that distinguish a particle from a wave, right? So what exactly is a wave? It has to be delocalized in space, and everywhere in space there is a value with the space-time that you can associate. What is a particle? If it exists on one point, you won't assign any value for its probability to find it in another point. So that is the junctional point, the area that you need to completely abolish in order for Copenhagen interpretation to take into the format so that it is consistent with quantum mechanics. But I completely understand that there are many expositions of Copenhagen that are misleading. Absolutely.
But I think in the end, it's the initial assumptions that create the problem. And what you have is you're building a house of cards. When you build a house of cards based on faulty assumptions, then the outcomes are even more ridiculous. I mean, the conclusions are more ridiculous.
So,
Anyway.
okay, good. we can definitely continue that. But only one thing is Copenhagen interpretation does not have any other assumption other than quantum mechanics. It's an interpretation. So, I mean, if you find any such thing, I don't think that's a good exposition of Copenhagen interpretation, because Copenhagen, you can completely not know Copenhagen interpretation by when you do physics, right? I can just use the equations and I can make use of it in describing any equation. For anything to become science, you have to tell me what experiment you are doing, which state you are preparing your system, how you are evolving it, and what exactly you are measuring. And after you measure, you get something experimentally. Now, I, as a theoretical physicist, have to come up with a theoretical model that does something, and then it gives you a result that matches with your experiment. The question is, where should I apply the falsifiability criteria? Should I apply it on my entire theory as a whole, or should I apply each and every logic that I used in devising my theory? And that's where I think philosophers or scientists, they differ quite a bit. In many theory, for each and every line or logic, they are not falsifiable or verifiable. But yes, this is definitely a broader discussion.
Also, I think we have to make a distinction between math and physics. And, if you know the history of quantum physics, Schrodinger was trying to make predictions. He started out attempting to make predictions with this equation, and turned out that it didn't predict trajectories of particles. And there's another comment that so then they had to come up with Born's rule and all these other mathematical artifices to make the so-called theory match the measurement outcomes. But we talk about Hilbert space as if it's an actual space, when in fact it's a mathematical construction. It really what Hilbert space are really just the harmonic components of the wave function, and they don't correspond one-to-one to a physical reality, although people talk about it as if it does. And again, quantum field theory has resolved a lot of this, but
Michael, I'm going to throw in on what you just said. The harmonic components are the part where Everett was extremely sloppy in his thesis, because he just assumed a Hilbert space was the only thing that existed. He assumed that as a de facto concept, but in doing so, he assumed infinite frequencies of infinite length. It's not just the frequency, it's how large is the frequency, how large is the band. Just like when we listen to a radio, you have to have a certain amount of frequency before you can define and get a precise fix. So what his Everett completely misses is the idea that you have to have unbelievable lengths of time to distinguish between the different states that he just casually assumed and said, oh, Hilbert, that's it. Which makes me wonder about your point that he may have actually been kind of pulling the leg on his professors, because he put that in there, but he didn't try to justify it. He made no attempt to justify it. He just made Hilbert space as a concept sacred. But that's not physics. That's not how waves work. Waves don't work that way in the real world. We have never witnessed waves in the real world behaving that fashion. Length of the wave train, the scale of it always makes the difference. Now, but after saying that, now I've got to come back with one for you. You mentioned that you feel that it's mathematically consistent to use the pilot wave, but every physical experiment ever done shows that points are infinite energy, and that waves, perfect waves, also require infinite time, infinite space. So do you really want to make the foundation of physics based on something that cannot exist? So what Joydip, if either or both of you will comment.
Yep. So first thing I would say that when you say that Hilbert space, the frequencies are infinite, the only comment is not only it is infinite, it's uncountably infinite.
Yes.
Now, when you say that the assumptions and the criteria that can go into the assumption and what is real and what is not, these probably require, I would say, a little bit of cultivation beyond literal reading of the way how quantum mechanics assumptions were written, because the problem is we have to define something called sensual assumptions, essentially, that assumptions that make sense based on our senses. Now, one way of thinking about it is, and I'm not sure if you can make sense of Hilbert space or not, but you can definitely understand the relationship between Hilbert space and its basis. And that is the point. The basis of the Hilbert space is the real space. Okay. Yes. Now, can we make sense of it by looking at a system where Hilbert space itself is finite? Well, there is one I can think about. So again, this can be a bigger discussion, but I'll just mention very quickly. Let's say you have a machine that can give you 0 if you are moving in north-south direction, and it gives you 1 if you are moving in east-west direction. Now you take that machine in your hand and you started moving in the northeast direction. What are you going to see? that cannot show anything other than 0 and 1. So it will fluctuate between 0 and 1. If you collect the statistics of the 0 and 1, you will see that the 50% of the time it showed 0 and 50% of the time it showed 1, right? So if you kind of extend that analogy, I don't have time to go over the details, but if you try to extend this analogy, essentially, you will realize that it's the same way that particular machine lives in its own space with two possibilities of 0 and 1. We are living in our space based on our sensory organs, which can only view the real space, which is just a basis of a bigger space. For that machine, northeast does not mean anything. For us, Hilbert space does not mean anything. But again, this is a broader discussion, but we can create this discussion within the realm of the way quantum mechanics is understood at this point.
One comment.
I'm sorry.
Sure.
No, you go ahead, Terry.
Sorry, Michael. I just one quick comment on Hilbert space that has fascinated me for years is that dynamics are impossible in Hilbert space, and I mean that from a mathematical perspective. The reason is this: if you're in a tunnel and a bomb goes off, you're dead, no matter which end of the tunnel you are, because there's no dispersion. If you're in a two-dimensional space, it goes over 1 over r. If you're in three-dimensional space, it's 1 over r squared. If you have a Hilbert space and you take it seriously, it's infinitely dark. Nobody can see each other. They can't see each other because the dispersion, the spreading, is infinite. So every point becomes isolated in that point. Now, this is something I've never seen this addressed to me, but really addressed at all. But I think it needs to be addressed. You can talk about it as a structure, but if you talk about it as a dynamic space, then you have to deal with the issue of infinite darkness. Now, what happens in the actual theories and actual calculations using Hilbert space is you simply cheat. You don't do that. You create an extremely small subset of the Hilbert space that you've sampled. And within that sampled space in which you made classical constraints upon the entire breadth of it, then you can calculate. And from the sampling, you then elaborate to the infinite space. You say that, well, I can sample here, sample here, sample here, sample here, sample, do all these sampling. So you do an infinite number of sampling and you get an infinite Hilbert space. But that's an abstraction. So you can say that's a model for how these things classify, but it's actually an emergent behavior that you're calculating each time. So Hilbert space dynamics, I think it's dangerous in any of our maths to be too simplistic about the dynamics of the math. It's easy to write a formula down and say, here it is. But in some cases, you want to be a little more careful about saying, what does that imply in terms of what would actually happen? Can I put real matter into that space? Can I put real energy into that space? And if you can't, you want to be a little careful about that formalism. So it doesn't give an answer, but it says, yeah, we should be cautious.
Well, Terry, you say Hilbert space is an abstraction, but all mathematics is an abstraction. It's just an attempt to correlate an explanation that our brains can understand to physical reality. And again, Schrodinger was trying to develop, a kinematic equation that would describe trajectories of real particles. And when it didn't work out, they had to come up with all these crazy, Born theory and probabilistic outcomes and all these other things that we determinists don't believe in.
But you do accept the interference, though, right? Like the double slit interference, you do accept that as an actual phenomenon.
Well, I accept the experiment.
Oh, okay. What I was saying, but that you do get these unusual results in terms of the.
But Bohm explains it differently. Bohm explains it differently. He says that there are multiple trajectories, and which trajectory the particular particle takes would obviously depend on the initial conditions that we can never measure. I'm
Ahead,
sorry.
I'm sorry. Go ahead.
And again, I think, you know, what Hilbert space is indicating is that, again, Hilbert space are the harmonic components of the solution. And I believe what it is leading us to is what it's indicating is that we need what ultimately became a quantum field theory, which says that everything is a field. And fields have harmonic components, whether you believe that they're, finite or infinite. Fields have harmonic components, and they're not localized at points in space and time. They're spread out in space and time. In fact, I don't even know what a point is in space or in time. A point is a mathematical abstraction that we learn about in high school geometry. But in the real universe, points don't exist.
And Michael, and even though I like the point that you're saying that by quantum field theory you don't have to worry about points, I agree, because you saw my comment or my earlier question that if you go to a point, we don't see that. That's why we have huge accelerators, just to approximate a point better. And if there's a shortcut for doing it, we wouldn't be doing those massive accelerators. There's a very, very solid experimental relationship between enormous energy and point-like behavior. Quantum field theory takes you out of that. However, quantum field theory has its own interesting problem, which is the gamma wave results from, I think, 1920. I'll put the reference in a little bit later. As soon as you go to quantum field theory, one way or the other, you're going to wind up with ultraviolet limits. You're going to have to, it has to be a resolution, it has to be a finite resolution to your fabric, to your quantum field. And pretty much, Penrose, in fact, Penrose accepts that so strongly that in a live weekly, that one they used to have, Astrophysica, he expressed real surprise at the gamma ray results, which showed that Einstein was right. There's no frame that's different from any other frame. That the gamma rays, no matter how intense they are, they didn't disrupt that finite quantum field theory. So quantum field theory network. So there's an interesting problem there, is all I'm saying. And I'll put a quote down on it.
Well, science is a work in progress. At every point in history, scientists or intellectuals have felt that, oh, we understand the universe now, and there's nothing more to learn. Yeah. Abraham Lincoln, President Lincoln, was advised to close down the patent office in the 1860s because people were convinced that everything that would ever be invented had been invented. But yeah, science is a work in progress. And again, we have to make the distinction between mathematics, a mathematical theory that attempts to explain reality, with the reality itself. So of course, quantum field theory is not complete.
Apologies, Joydip. We got into a dialogue. Back to you. Sorry, sir.
So science is also about continuing illuminating these discussions that we are doing. Just I will make one comment and then probably I have to go, and we can continue that offline too. So infinities bothered people. So I intentionally avoided the discussion of quantum field theory. I don't think quantum field theory solves any of the philosophical issues that quantum mechanics has. It just puts them under the rug of the single node of the Feynman diagram. But I don't want to go to that because it can bring a broader discussion. Let me give you a very quick example from a classical mechanics, where how infinities can bother us. So let's say you have a ball that you can drop on a floor, and Newton used to call it the coefficient of restitution. What it means is the height from which you are dropping it and the amount of height it bumps out of. Okay, so let's say the coefficient restitution is half. So if you start dropping it 1 meter height, it will, after the first bump, it will rise half meter, right? What about after the second bump, 1/4? This exactly mimics the ancient Achilles tortoise paradox. We can ask two questions. The first question is, after how many reflections from the floor it will stop? And second is, how much time it will take to stop the ball on the floor? So the answer to the first question, that after how many bombs from it will stop, the answer is infinity. If you calculate the time, this is finite. This is something that we study in high school physics probably, or college level physics. But what is going on here? It will take infinite amount of reflection in a finite amount of time. And also the magic is reflected from the math as well, right? I can create a convergent series with infinite number of terms in it, but the result is finite. But that is the math versus physics. But how can I make sense of it? What is going to happen in reality? So let's say the ball is making a sharp sound at every time you drop it on the floor. Now I can count those sounds, tick, tick, every time it drops on the floor. How can I count infinite number of such ticks? What happens at the very end is you will hear a continuous sound like that means that's where the infinity is buried inside. So it not necessarily, yes, it bothers us, but it doesn't necessarily always mean having infinities. We cannot make sense out of it. Of course, there will be a philosophical aspect that will challenge humanity, and we will move around that. But just to kind of give you a point using classical mechanics alone.
But again, doctor, infinity is a mathematical concept. And when we get a solution of infinity that attempts to describe a physical theory, that is an indication of a breakdown in the mathematics to describe the theory. And yet, we have respected scientists today telling us that there is infinite curvature at the center of a black hole, for example, because that's what the mathematics says. No, infinities that describe physical phenomena are just illustrating a breakdown in the mathematics.
Great. Yeah, let's continue it. I will probably have my email address and etc. if you wanna discuss this further. Unfortunately, I had to leave in a few minutes, but I enjoyed this entire conversation.
Thank you.
Thank you.
Sure, I will forward some questions to you. Yes, I see some questions. Yes, or maybe can you
Sure.
take
Yep.
one question? Simple question.
Yeah, we can take one question. Yes.
Sure, it's from Jordan. The quest to identify quantum advantages, complexity theoretic conjunctures. What are your thoughts on these new domain problems in QC or QIS?
Okay, first of all, let me first understand quantum, in order to build a quantum computer and in order to establish that quantum computer can do stuff that is beyond the realm of classical computer, yes, you need a complexity theoretic argument. And that's where the efficiency comes into the picture. So whatever we know today, that there are a class of problems, there's a technical name for it called abelian hidden subgroup problem. But there are class of problems for which people have discovered quantum algorithm in mid-90s. For example, Shor's algorithm, where Shor showed that a few abelian hidden subgroup problem like discrete log or factoring a bigger numbers, which are very relevant for cryptography. If you have a quantum computer under the assumption that you have a quantum computer following all the criteria of quantum computing, then you can run his algorithm in that machine and factor bigger numbers quickly, very naively speaking. Whereas the best known classical algorithm, the number field sieve and all its variants, they are exponential. In that sense, quantum, there is an advantage that you can think of if there is a quantum computer that is built. Just know there is a caveat that there is no proof that in future one cannot come up with an algorithm for a classical computer to efficiently factor a bigger number or solve a discrete log problems, right? So that's an assumption. Number two is where there is a proof. For example, if you are trying to find a number from an oracle, and I don't want to go into the concept of computer science here, but let's say some searching problem. it is shown that by Grover and others in mid-90s that there are quantum algorithms that can be quadratically faster than best known classical algorithm. But it is not only about the best known classical algorithm. They showed that you cannot come up with a better classical algorithm that is the best possible classical algorithm that we can and we will have. And the quantum will always be quadratically faster. But remember the trade-off here. It is quadratic versus exponential. And that's the bigger deal. So people can always argue that we don't want to consider the quadratically faster problems because I will scale my classical computer quadratically and then I can compete against a quantum computer. And that's the debate that happens in the community with the broader industry segment and etc. But these are the different advantages that we know as of today. Super polynomial or exponential and sub-polynomial such as quadratic. There are others, but those are little technical.
Yeah, since Dr. Ghosh has to leave, I will forward Keynote Winter's 2 questions to you in email, so maybe you can keep in touch with him. And otherwise, yeah. And if you have more topics to discuss, you're welcome to come back to present your topics next year.
Oh, great. Thank you.
Yeah.
Yeah, thanks, Joydip.
Thank you. Thanks, everybody, for this wonderful discussion that we had.
Yeah, sure. So see you guys on December 6th with Terry Bollinger. Thank you for coming. Goodbye now.
Thank you. Bye.